Chris Morrone, ladies and gentlemen.
Thank you. So I'm going to tell you a little about the latest supercomputer that we have at Lawrence Livermore National Lab. It's Sequoia, hiding behind the handsome figure in this photograph. It's an IBM Blue Gene Q machine. It's the third generation of Blue Gene machine that we have at Lawrence Livermore. It's a PowerPC-based supercomputer. Before that, we had Blue Gene L and Blue Gene Q, Blue Gene P, sorry. Sequoia is a 96 racks of computer. Within each rack, we have 1,024 nodes. And each node has 16 compute cores. So that gives us a total of over 1.5 million cores, and they all want to use Lustre, so that's a big challenge for us. To get that many nodes into a single rack, we have a node that's about that big on a card. We fit 32 of them onto a single tray that the IBM calls a node card. 32 of those trays go into a single rack. That gets us our 1,024 nodes. The hat at the top of the rack, that black box, houses the I/O nodes. In our configuration, we have 8 nodes there. The I/O node and the compute node hardware is exactly the same, except that it's water-cooled for the compute nodes, and I believe it's air-cooled in the I/O nodes at the top. There's a picture of all the racks in their glory off into a distance. The 128 compute nodes all have to communicate with the file system through a single I/O node. This is my artistic representation of the torus network. It's actually a 5-dimensional torus. But what's important here is that there's only 2 links to each of the I/O nodes. All the other compute nodes have to funnel their I/O traffic, over the torus network to get to the I/O nodes. IBM has a very lightweight file system that runs on the compute node. It's not a full version of Linux running there. All of your operations, your system calls, need to be function shipped over to the I/O node. And the I/O node is where you actually run Linux and the Lustre client code. So the Lustre client here needs to handle a lot of load that might not normally be seen in a typical Linux cluster, because we have potentially thousands of different files and threads that want to read and write to Lustre at the same time through a single Lustre client. The file system we built to take care of all that data is 55 petabytes in size. We've measured it at 850 gigabytes per second during sustained write performance. Our goal there, our minimum requirement was 500. Our stretch goal was 1 terabyte a second. So we easily exceeded our minimum, but we're still trying to hit the target of 1 terabyte a second. And I'll go into a little about what our problems are there in a moment. The file system we built, we have only a single OST on every OSS. That's really nice for us. In the past, we used to have as many as 15 OSTs per OSS, and that gets a little difficult to administer. Each one of our OSTs is 72 terabytes in size. The basic building block for the file system server side is 2 OSS nodes that talk to a single NetApp E5460. We arranged the 60 drives into 6 LUNs. Each one of the LUNs is 10 drives, RAID 6, using the NetApp hardware RAID. And then we grouped them together in software, 3 of them, to make a 72 terabyte OST. Each one of those basic building blocks, we put 8 of those into a single rack. You can see the rack on the end there. We have 8 of the NetApp enclosures, and at the top we have an Apro Blade data center that we use to house the 16 OSS nodes. We combine those all through mainly 2 648-port QDR switches. The OSSs connect half of them to one of the big switches, half to the other big switch. That doesn't leave enough ports for all the I/O nodes to connect. We have an equal number of OSS nodes and I/O nodes, 768 of both. So what we do is we have a bunch of ion leaf switches, 64-port QDR switches. 24 of the IO nodes connect to a leaf switch. Then there's 6 uplinks to each one of the bigger QDR switches. And this turns out to be the point of one of our problems for our performance. Naively, you might look at this and do the math and go, oh, you should be able to get 1.5 terabytes a second. What turns out is that we have a problem with the way you lay out the static routing with an IB network like this. It's very difficult to make sure that you're evenly using all of the links all the time, because Lustre, left to its own devices, will more or less randomly pick which OST a particular client is talking to. And that can lead to situations like within one of the leaf switches, you wind up using one link by 10 files, and then other links are not used at all because there's no coordination between which one of the links goes to which one of the OSSs with Lustre. Some of that can probably be mitigated through clever using of laying out your routes, but the problem is the OpenSM, the subnet manager for InfiniBand that we use, has kind of naive algorithms for laying out the routes. They're more appropriate for a compute network where you would have all of the nodes potentially talking to another node. On a network like this, a storage network, we know that the IO nodes need to talk to the OSSs, but the IO nodes aren't talking to each other. The OSSs aren't talking to each other. So we really need to set up those static routes before we create any other routes that we're not going to be very likely to use. We've seen problems, for instance, reading. We'll notice that one of the OSSs is going at 50 megabytes a second. All the others are going at 800 megabytes a second. As soon as the traffic ends and the rest of the guys stop writing, that guy that was going at 50 jumps up to 2 gigabytes a second and then finishes. So clearly there's some congestion there that we need to track down and find out why that particular guy must have slightly different routing than everyone else. But the big story here, for us at least, and I think for Lustre, is that OSD ZFS is now a reality. If you've come to these LUG meetings in the past, you've heard either Brian Bellendorf or myself standing up here talking for years about how we're going to have OSD support in Lustre, we're going to have ZFS support. It's finally a reality. The code's actually on the Lustre master branch, and you'll actually be able to use it with Lustre 2.4. Since 2007, we've been planning this. There's a lot of architecture work that needed to go into this, so it was a tremendous amount of work. Originally, we had planned to have the back end of Lustre be more or less a general API that any back-end file system could use. But over the years, it became very tightly intertwined, and it wasn't really possible to plug in another file system. So this was a culmination of a lot of work to actually split those apart again, have clean APIs between Lustre and the back-end disk. And Livermore contracted with Wham Cloud at the time, now Intel, to complete that work, and they deserve a lot of credit because that was a tremendous amount of work to do that. I'd like to point out and mention OSD is not just for ZFS. If it was just for ZFS, we probably could have taken some shortcuts and made it a lot easier on ourselves. But the OSD work actually addresses a lot of technical debt that's existed in Lustre for years. Enables a lot of new features that you're going to see come down the pipe. The D&E work in 2.4 requires the OSD work. If people want to use ButterFS in the future, there's a lot of people have shown some interest in that. ButterFS would need this work to be completed as well. You've probably heard these before. We've talked about this a lot very briefly. Some of the benefits of ZFS are that it's a copy-on-write file system. So that means that all of the random writes that a back-end file system sees, and no matter how well formed the I/O is from your application, by the time it gets to the OST backend in Lustre, that data all looks random to the disk. What ZFS can do is take all those random streams, merge them together, and sequentialize them before they go to hard drives, so you can get much better bandwidth out of your hard drives than you can otherwise. A normal spinning disk, you're generally constrained by the IOPS rate, how many operations you can perform. And if you can perform larger operations by merging them together, you can get a lot better bandwidth. ZFS's file system limits are much larger than we've had with LDiskFS. We have no problems going to much larger OSTs. That makes management easier. It means less memory used on all of your clients. The first time we mounted an early 2.1 client on our file system, we had roughly 3,000 OSTs, I think, and the Lustre client wound up using over a gigabyte of memory at mount time. So anything we can do that we can reduce the number of OSTs has benefits all along our stack. Offline FS check time. Every time we have a failover with LDiskFS, we have to do a fairly lengthy LFS check before we trust it to put the file system back into production. And that's even if we're doing kind of the minimal FS check, not doing a complete exhaustive FS check. With ZFS, the FS check is online, and all the consistency and error handling can be online. That's a great benefit for us, speeds up our recovery times. ZFS, without doing any real extra work with it, already supports very scalable directories. I've personally tested having every single core on Sequoia open and write to its own file in one directory. So it takes a while. The MDS isn't as fast as we'd like to be right now, but it works. ZFS has a lot of additional benefits that we knew about, but didn't necessarily see initially how they were going to be useful for Lustre. Compression is one of them. We're like, well, it seems like a good idea, but what impact is it going to have on performance? It turns out not much. Performance stays about the same with compression turned on, but you get compression. It really saves you space. We have over 400 million files in our file system already, and that's only 5% of the file system, not even. And we're averaging around 1.7 to 1 compression, so we're clearly saving a lot of space. They have some educational side effects, though, because people look at their files, do an LS, and go, oh, my file is this size. I'm going to start moving it to this other slow thing, and I know it goes about this speed, so it should be done in half an hour. They come back in half an hour, it's still going. It's written more than I thought it would. Well, it turns out the actual size of the file when it comes out of the file system is 3 times bigger because their file was very compressible. So there's some learning that has to happen there, but it's been a very nice benefit. Snapshots, this has been great for the developers especially. I don't know about you guys, hopefully most of you don't have to do this, but I've certainly in the past year had to be woken up at 3 in the morning and edit the backend file system with a hex editor to get Lustre back into production. That's kind of scary with LDiskFS because we don't have a way to back up our LDiskFS file systems in any sane way. With ZFS, we're running a development branch right now, and we've had to do a little of that because it's the development branch. But it's been much easier because we can take a snapshot very easily with ZFS, make our changes, and know that if we screw it up because we're editing things by hand, we can always go back. So we've got an extra measure of safety there. We've also used the capability. With ZFS, you have pooled storage. So a file system, multiple file systems can be created within the same backend storage device. This has turned out to be great for Sequoia for testing because we set up the one file system that all of our users used, and then in our weekly 1 day of full system testing that they gave to us early in the development process of Sequoia, we could shut down that file system, bring up a new test file system on the same storage devices, and know that we're a little less likely to screw up the user's data because we're using different file systems. In the future, some other ideas we've had, being able to use ZFS send and receive to do backups or copies of your file system, and perhaps maybe even snapshot the entire Lustre file system using ZFS snapshots. You'd have to do some scripting to coordinate all that. You'd have to do that offline, but it's a possibility. So you're probably wondering, what is the status? Does this actually work? And we are using it. Like I said, we have over 400 million files of real user data on the file system right now. The OST over the ZFS, I'd say stability is good, performance is good. And the OST performance has probably exceeded our expectations because the backend device can probably handle a little over a gigabyte a second. With compression, if your file system's your data is compressible, we've seen the OST do 3 gigabytes a second. So we can actually handle ingress over the data, over the network, far faster than the back-end storage can actually handle the data. The MDT stability, again, its stability's been pretty good. Performance could be better. Right now, we're only doing around 6,500 creates a second. That definitely needs to be improved. Accessing data is much faster. The surprise for us, actually, was how much effort we've had to put into the Lustre client. None of the client was affected, really, not significantly, by the OSD work, but most of our effort has gone into making the Lustre client be able to handle the workload that we're putting on it. And that's one of the reasons we haven't had time to go back and work on the MDT performance yet. So ZFS, we didn't really need to, but Brian Behlendorf ported all of ZFS to the Linux kernel. He could have stopped at a lower level of ZFS because we don't need the POSIX file system to make it work with Lustre. But he went the extra step, he packaged it and ported the entire POSIX ZFS layer for ZFS. And that has the benefit that we now have a vibrant and growing community of ZFS on Linux users. It's grown to a point where we have external developers popping up, contributing good code to ZFS project. We have people that have popped up and are packaging it for every Linux distribution under the sun. Half of these I hadn't even heard of before I looked at Brian's list. A lot of this credit goes to Brian, again, because he's done an excellent job with the packaging and the build system for ZFS on Linux. But because he's done that, a lot of other people have come out, and you can find Ubuntu PPAs if you want to install ZFS very easily that way. You can find Yum repos for ZFS. Just to give you an example, Brian this week went to the extra effort to create a new spec file for Lustre to make it possible to use DKMS to build the entire Lustre server. So here's how you can install Lustre using ZFS. Just 2 commands. The first one is just to initially set up the Yum repos and the signing keys so Yum knows where to find Lustre in ZFS. And then it's 1 command, sudo yum install Lustre. That'll grab the Lustre packages, the dependencies there will grab the ZFS and the SPL packages. DKMS will build all of the modules, and you'll be ready to go. So we think that shows what we can be doing with Lustre in the build system and the way we can be distributing packages. And I hope that in the future we'll continue to improve Lustre upstream so we'll be able to make it just as easy for everyone to install Lustre. But in the meantime, you don't have to patch your kernel. ZFS requires no kernel patches, so you can try it with your stock RHEL kernel. And if you want to try out ZFS, there's instructions on ZFS on Linux. There's instructions for using it with Lustre as well. And feel free to talk to myself or to Brian Behlendorf, who did all of the ZFS work. That's all I have. Thank you.
So hats off to you and to Brian for seeing this through. I mean, you know, it's been a long slog, but rock on.
Thank you. Any questions?
I've got a question. Sorry. Go ahead.
Hey, Brian. So you said that we're having client problems, but that's unrelated to ZFS, right? Or is it?
That's correct. It's really unrelated to ZFS work and the OSD work. The biggest problem for us was the move from 1.8 to 2.0. The CLIO, the client rewrite, there's a number of regressions and bugs and new performance problems that came out of that we're working on. And Jinshan deserves a lot of credit. And at Intel, we've been working on a lot, and Jinshan's had a lot of patches for us that address a lot of the problems. But there's still a few more that we still need to address to really get the performance we want out of the client.
And then the MDT performance issues. So why not just continue to use LDiskFS for the MDT?
That's probably possible for people. We're pretty committed to ZFS route, so we like the uniformity of having the same software installed everywhere. And I do believe that most of the MDS issues are probably fairly low-hanging fruit that we can address.
I can make a couple comments
Mark
on that
has,
as well.
Mark Stearman from Livermore.
Yeah, some of the advantages that Chris mentioned about ZFS are really important on the MDS, like the lack of having to do an FSCK. On our systems, that takes 5-6 hours. With ZFS, it takes 0 because it's all online. We also get redundant metadata copies, so we can do ditto blocks of all of that metadata, so it's more reliable. It has the checksums, no FSCK. I mean, there's a lot of advantages to using ZFS for the metadata server. Also, I think some of the problems we were having with the client were due to PowerPC issues, which is what all the I/O nodes are. So, swapping and all that fun stuff.
We frequently hit problems with the PowerPC, but those are relatively easy things to fix. Those are generally fairly obvious. The performance problems are kind of the higher hurdle. They're more difficult to solve.
I have a question. So consider that the Sequoia system is based on a Blue Jeans system. I was wondering whether you had, at least originally, some tests with the GPFS file system.
We did not do GPFS, but we do have some comparisons. Argonne has a similar machine. I believe they're running GPFS and have some comparisons there. I don't know the full details of what their numbers are. Bulk data-wise, I think we're pretty darn competitive. Metadata, I don't know if we're quite as good right now. Yes, so you can turn on compression algorithms. ZFS has several compression algorithms. You can turn them on and off on the fly, whether or not you want the file system to enable that. And right now, with the compression algorithms we're seeing with real data, we're seeing 1.7 to 1 compression on average.
Yeah, and that's the key. It's on average. There's some, I've seen some files that were compressed, like 42 to 1, right? All those text files just compressed really small. Binary blocks not as much, but on average 1.7.
Yep.
I have a question. So I've noticed that there's a difference in the changelog structure between like LDiskFS and ZFS. So if you want to write a tool, say like Robinhood, who looks at this, is it compatible, or do you have to write actually different cases for both of the file systems?
I don't know much about changelogs there. I would actually hope that they'd be pretty similar, and if they're not, we probably need a bug open.
So I got a question.
Yeah.
The last time I checked in with this work, Brian gave a talk, and he was comparing the difference between using disk controllers and not using disk controllers. Can you comment on where that's at?
Sure. For this time around, we did use hardware disk controllers. We're not using the software RAID of ZFS. Brian and I certainly feel that's the future, and that's where we'd like to go with the next generation of file system hardware we have. Certainly, there's a lot of concern at Livermore about all of the things that you get with general monitoring of hard drives, failures, things like that, that we'd have to replace if we got rid of the hardware RAID controllers. So right now, that's our migration strategy, is to begin with ZFS on top of the hardware RAID controller, and then work on all of that extra infrastructure that we need to monitor and tell our admins that a hard drive is dying and needs to be replaced and turn on a light. All of that would need to be replaced if we got rid of the hardware RAID controller and the software provided by the vendor. So right now, we are actually on the MDS. We are not using hardware RAID. We are using ZFS's built-in RAID. There we have something like 24 SSD drives in a ZFS mirroring setup.
42 drives.
42, oh yeah.
Yeah, it's 24 pairs.
There you go. Thank you. 24 pairs, so 48 total drives, and that's all ZFS software RAID.
Actually, I'm not asking a question, so I'd like to put a word on client I/O performance. So recently, I'm working with Ihara tightly about the performance tuning. So with my latest patch, the client can saturate QDR network easily. Yeah, and with FDR, we can reach around 5 gigabytes per second from a single client. But I agree, we have a lot of room to improve the performance. But right now, I think client I/O performance is okay for most of the customers.
Yeah.
Thank you.
So in more detail, I think if you're doing file per process and you have multiple threads writing to different files from a client, yeah, the performance is actually pretty good, and that's the bulk of our users. But some of the users from other labs have shared files, and if you have 128, 1,024 threads on one client trying to write to the same file, there's a very big regression in the Lustre client right now that will prevent you from getting good performance. It's very sequentialized right now. So there are certainly a lot of modes where it's working fine. There's certain workloads where it's still problematic. I think both. Write is the immediate problem right now. That's the bigger concern, but read performance also has its issues. Read we've seen a lot of weird things where the client performance is very stuttery. It starts and stops. The servers are very lightly loaded, and the client just seems to not be requesting enough data. It starts and stops. We haven't had time to fully investigate the problems there.
Okay, we're at time. Thanks, Chris Morrone, and thanks,
Thank
Brian
you.
Behlendorf.
Yep.